right, thanks a lot for having me back. It's great to be visiting here. So I'm going to tell you about some recent work with Greg Mathis, who is a postdoc at Cornell and has recently moved to EPFL. We had a couple papers about this in September, and we have some work that we're continuing with. So the subject here is the Aboriginal energy operator and the constraints that it gives us on field theory. I don't know if I can get rid of this not hearing anything. It's kind of, let me try. There we go. Okay, so the Aboriginal energy operator is the integral of the null components of the stress tensor over a null ring. So that's this operator that I'll call squiggly E sub U. U is the null direction. And this operator has shown up in many different places in quantum field theory over the years, and especially recently. It's connected to quantum information and QI inequalities because this operator shows up in deformations of the modular Hamiltonian. It's related to correlation functions because this operator shows up in the operator product expansion when you take two local operators and you move those two local operators to be nearly null separated. So as you take them to be null separated, you get operators like this that contribute to the OPE. And therefore, these operators control correlation functions and scattering amplitudes in some kinematics. It's a very interesting operator because of positivity. So this operator is positive. It obeys the Aboriginal energy condition, which is a statement, just the statement that it's positive. And so it's been used together with its connections to correlators and quantum info to derive constraints on coupling constants in quantum field theory, on OP coefficients in conformal field theory, and on quantum information. What I want to do in this talk, and I'll describe to you, is adding a new link to this list of nice things that the null energy operator can do for you, and that is to reproduce the C theorems in D equals 2 and 4 dimensions that govern renormalization group flows. So I am going to start with an introduction, which is really more of an advertisement for C theorems and an advertisement for the Aboriginal energy operator and all the nice things it can do for us. And in particular, I want to talk about why I still think the C theorems are really interesting and mysterious. This is an old subject that goes way back, but I think there's lots of open questions about it and useful things that we can do with it. And then I'll get into the new stuff. The goal of the talk will be to get to this. So this is to rederive the four-dimensional A theorem, which I'll talk about, from the Aboriginal energy condition. So that's what we want to get to. We're going to work our way starting with C theorems. Good. So C theorem, what is a C theorem? When we think about a quantum field theory, we can think of that if the theory is fully well defined in the UV and the infrared, we can view that as a renormalization group flow between a UV CFT and an infrared CFT. A C function is something that satisfies, it's a quantity that satisfies two properties. First of all, at a conformal fixed point, it must be universal, in the sense that it depends only on the CFT data. It's not allowed to depend on how you got there or the renormalization scheme. It has to be defined intrinsically in terms of the data of the CFT. And secondly, it is something that decreases under RG flow. So if you have an RG flow that connects to fixed points, then the value of C at the endpoints needs to go down. So if you find a function that satisfies these properties, then you call it a C function. Now, if a C function exists, then that establishes that the renormalization group flow is irreversible, it's monotonic, because you have this decreasing function on the space of theories. So this subject goes back to Zamolodchikov, who introduced the little c theorem in 2 dimensions in 1986. So first, some word about the terminology and the letters here. So when I say big C theorems, I'm referring to this broad class of possible constraints and various dimensions. Whereas the little c theorem, so this is the original one, little c is the central charge in a 2-dimensional theory, and little c, the big C function flows, is a flowing version of the central charge. It flows to the central charge at fixed points. So the way Zamolodchikov proved the C theorem, the original C theorem, was by studying the 2-point function of the stress tensor. In particular, what he did is he took this, the 2-point function, imposed positivity, flexion positivity on this 2-point function, combined that with the conservation laws satisfied by this 2-point function, and turned that into a flow equation for some quantity, the C function, used that to infer the C function and the C theorem. Going up in dimensions, the A theorem in 4 dimensions was much more difficult to prove. So this was conjectured by Carty back in the 80s, but it wasn't until 2011 that Komargatsky and Schwimmer proved that there's a decrease of A along RG flows. So A is related to the conformal anomaly in a 4-dimensional CFT. The derivation of the A theorem of Komargatsky and Schwimmer is very different from the method of Zamolodchikov. So instead of looking at the stress tensor 2-point function, which doesn't have any A's in it, they looked at the S matrix of the dilaton. They coupled the theory to a background dilaton, and then they looked at the S matrix for the background dilaton. You can roughly think of this as studying the correlation functions of the trace, but you could think of this as studying the trace 4-point function. It's not quite true because there's some change of variables going on between the dilaton and the trace, but roughly speaking, they're probing this trace 4-point function. So I'll use big theta to denote the trace of the stress tensor. The C theorem in 3 dimensions, the capital C theorem in 3 dimensions is called the F theorem. And this one is even more different and took 1 year longer. So the C theorem in 3 dimensions, so the F theorem in 3 dimensions, so F is defined by doing the path integral of the theory on a 3-sphere, or it's a quantity that you can define in terms of entanglement entropy of a spherical region. And there's an argument for there's a derivation of the F theorem by Cassini and Huerta, which uses a totally different set of techniques and boils down to strong subadditivity of the quantum entropy. In D greater than 4 dimensions, we don't know if there's a C theorem or not. There are lots of interesting partial results, including by Thomas and collaborators on supersymmetric theories. There are perturbative results in both in ordinary perturbation theory and conformal perturbation theory. So the evidence is that there probably is an A theorem. So this same anomaly coefficient is probably monotonic in 6 dimensions, but there is no general derivation beyond perturbation theory or supersymmetry. So that's the status of this subject, but I want to convince you that these C theorems, despite all these results, are really still fascinating and mysterious, because after all this time, we still don't really know why they hold or how generally. Because the words people usually say when they talk about C theorems is they say that, well, C measures degrees of freedom. And in the Wilsonian point of view, you're integrating out degrees of freedom to do the RG flow. Therefore, the degrees of freedom have to go down. Well, all those words sound good, but they're not really related in any obvious way to these actual quantities that are flowing. So in 2 dimensions, they are. In 2 dimensions, it's very clear that the central charge is related to degrees of freedom. It's a leading term in the entanglement entropy, shows up in the thermodynamic free energy. But in higher dimensions, these words don't really have any obvious connection to the actual theorems. In particular, why A? So why should A, this particular anomaly coefficient in 4 dimensions, a priori, there's no reason to say that that's counting degrees of freedom. If the A anomaly for a free fermion in 4 dimensions is 11 times bigger than the A anomaly for a free scalar, why should a fermion in 4 dimensions have 11 times the degrees of freedom of a scalar? So clearly we're not fully understanding what it means to measure the degrees of freedom. We don't understand why this counts the degree of freedom. We don't have a universal explanation that works in all dimensions. What we have is this sort of different, you have to think about the problem very differently, and there's different proofs in all the different dimensions. The closest thing to a universal explanation, I suppose, is the quantum information approach. So this quantum info approach works actually not only in 3 dimensions. There's a quantum info argument in 2, 3, and 4 dimensions. But again, it's some sort of mysterious magic of combining inequalities until you get something that works. But it stops working once you go above 4 dimensions. The reason for that is that in the quantum info approach, you're talking about entanglement entropies. And the higher you go in dimensions, the more divergent those entanglement entropies are. So the harder it is to get at the universal piece of the entanglement entropy, because you have to somehow get rid of all these divergences. And if you go above 4 dimensions, you run out of entanglement inequalities and can't prove the C theorem. The situation is also better in holographic theories. So in holographic theories, there's a really nice universal simple argument for the C theorem that works in all dimensions due to Myers and Sinop. But we don't know the CFT dual of that argument, so it relies on some energy condition for the bulk matter. And since that has not been translated into a CFT argument, it's just restricted to holographic theories. Still, I think leaves this subject open of understanding what is the origin of these C theorems. Okay. Any questions so far? So the other thing that I want to review is the average null energy condition. So the average null energy, as I said, is this light ray operator. I'm working in Minkowski coordinates U and V, which are null. And I'm always going to insert my average null energy through the origin. So I'm not going to put labels on it, but it's always just the null energy integrated over this null ray. This is an example of a light ray operator. And it's an operator that, as I mentioned briefly, has showed up in lots of interesting different places. I think the relatively modern point of view on this was started with a paper of Hartman and Malasena on conformal collider physics. It showed up in various other places. I won't go through each of these, but I'll just highlight one of them, which is timely. So the average null energy operator and the correlation functions of this operator are an alternative way of thinking about IR safe observables in QCD. And in fact, the correlators of this light ray operator are now the best way of determining alpha strong. So this is a recent preprint of CMS. And the best way of extracting alpha strong is now from these energy correlators. The average null energy is a positive operator. It satisfies the ANEC, average null energy condition, saying that this is positive in any state. This is not quite a theorem, but it's close, and in some cases it is a theorem. There's a long and interesting history to the ANAC. The early motivation for this statement came from GR. So when people were studying things like the singularity theorems and causality in GR, et cetera, back in the 80s, they always need to assume some energy conditions on the matter. And the problem is that in quantum field theory, there are no local energy conditions. Any local operator is unbounded from below. If you really want to have an energy condition that's true, then you have to consider non-local operators of infinite extent. Now, you could talk about the total energy, but the average null energy sits somewhere in between. So it's not a conserved charge. It's not like the total energy, but it's just non-local enough that it can evade this problem of having operators that are unbounded from below. And so it turned out to be good enough to prove a lot of these GR theorems. And then, well, they were considering various other possibilities, but then you start calculating expectation value of this operator in various theories. And it was the ANAC that seemed to actually be true in quantum field theory. So in the 80s, it was proved in free theory by direct calculation. You just have to show, you write it in terms of A's and A daggers, and you have to show that it's a mod square of something. It was proved for 2D CFTs. More recently, there are two derivations in interacting quantum field theory. The first one uses quantum information. This thing shows up in the modular Hamiltonian, as I mentioned before, and then you use entanglement inequalities. The other one uses conformal bootstrap methods and analyticity or causality of correlation functions, and leads to the same conclusion.
So the stress tensor is always the one that couples to the metric.
That's right, yeah.
Sorry, does it have? Well, yeah, if you have an improvement, some of the improvement might drop out.
Well, the ANAC. Improvement terms in at least in 4 dimensions and below don't contribute to the ANAC. But I am going to use, so for these I guess they're going to drop out of the ANAC. Yeah, that's right. Okay, so now turning to the new work. So first of all, the new results that I want to tell you about are that the ANAC implies the C theorem in 2 dimensions and the A theorem in 4 dimensions. Okay, so these were the C theorems that these are 2 of the C theorems that we already had. So we already knew there was a C theorem and an A theorem. This gives you a new way of deriving them, a new perspective on the C theorem and the A theorem. The way that I'm going to show this is to derive some rules for the change in C and A along an RG flow. Okay, so this is the other new result. And let's look at one of these sum rules. So to get all the ingredients here, this is the sum rule for the change in the central charge C in a 2-dimensional RG flow. So left-hand side, it's the change in C along the RG flow. On the right-hand side, the thing that's showing up here is a Whiteman function in Lorentzian signature of the trace null energy trace. Okay, so it's some integrated 3-point function integrated over some portion of Minkowski space. The sum rule in 4 dimensions is very similar. So now it's a sum rule for the change in A along an RG flow. And the only difference is the integration kernel. Okay, so you get some extra kernel that depends on the transverse directions in your integral, but otherwise it's basically the same. The correlation functions that are showing up here are the correlation functions of the QFT, of the theory that's flowing between the 2 CFTs. So the fact that you're doing this integral over Minkowski space probes all the different scales of the RG flow because this is the flowing correlate. Another more conceptual way of thinking about this is that these sum rules are relating some terms that show up in the effective action of the infrared theory to correlation functions involving the light ray operator. The way I've written this, I have not actually written it in terms of the light ray operator. I just wrote it in terms of TU of 0. But you're doing all these integrals, and you can use translation invariance to move the integrals onto the null energy, write it in terms of the light ray operator, and that's how I'll do it when I derive the sum. So that's what we want to do, and what I'm going to do in the rest of the talk is to explain where this came from and how we derive this. One last comment while we have this up is that so Zamolodchikov in 2 dimensions used the 2-point function. Komor-Gaussian-Schwimmer in 4 dimensions used the 4-point function. So ours is using the 3-point function in both cases. So in a sense, it sort of sits between the arguments of Zamolodchikov and Komor-Gaussian-Schwimmer. If you take our sum rule in 2 dimensions, then it turns out that you can pretty easily turn this into Zamolodchikov's result. So in fact, this is exactly equivalent to a Euclidean sum rule that Zamolodchikov derived, whereas the case in 4 dimensions, it's much less clear how it's related to either Zamolodchikov or Komor-Gaussian-Schwimmer.
So these integrals are convergent.
These integrals are convergent, yes. Well, they're convergent if you insert a wave packet and then take the wave packet infinite size at the end. So we're going to use distributions along the way. You have to put in a cutoff, and then there's an infrared divergence that drops out.
I have a very dumb question. The red dot product, why is it obviously positive?
In this, the way I've written these, they are not obviously positive, and I'll come back to that when we talk about the A theorem. Yes. In 3, did you say? We don't have a 3 dimensions one. So actually our method only works so far in 2 dimensions and 4 dimensions. And the reason for that is that we're going to use a conformal anomaly, and we don't have a conformal anomaly to work with in 3 dimensions.
What about 6 dimensions?
In 6 dimensions, you can try it, but it doesn't work so far, at least. There are some miracles that have to occur in the derivation. Maybe after I do it, if you want to know what the miracles are, I will come back and answer that at the end. So far, it doesn't seem to occur in 6 dimensions. Yes.
Dumb question, but why are we inspired or motivated to find this theorem in 5th dimensions or above?
Well, so one reason is just that we want to understand what quantum field theories can exist. And there are interesting quantum field theories in 5 and 6 dimensions that come out of string theory. I'd like to understand what they can do. But maybe so that's one reason. From my point of view, I think my reason is a little different. It's more that I don't really feel like we understand it if we have to do a different argument in every number of dimensions. I feel like if there really is a universal C function that exists in all dimensions, like there is in holographic theories, so this is not crazy. If this really exists, then we should have an argument that's independent of the specific details of the dimensions, and then it becomes an important problem to try to understand 6 dimensions. Now, I'm not going to solve that problem because our method doesn't work in 6 dimensions, but that's what I have in the back of my head in trying to extend it to that case. That's cool. Are there other questions? Okay, so I'll start by describing some general properties of correlation functions involving light ray operators. So as I said, now our goal is to get to here, the A theorem from the ANAC. This is a 4-dimensional case. The 2-dimensional case is very similar, so I'm just going to focus on 4 dimensions for concreteness. The object that we're going to be studying is a retarded 3-point function. So this is 3-point function that you can think of as a second order response of the null energy to insertions of the trace. So this 3-point function is defined by step functions times commutators. However, when you write an expression like this, it makes sense only at separated points. So when the points are non-coincident, like these step functions make sense, but you can't define a retarded correlator at, there can be contact terms, delta functions that show up here, and then it doesn't even make sense to try to write it in terms of step functions. You have to define those contact terms another way. But ignoring the contact terms for a minute, if we take this 3-point function, then we can integrate the stress tensor over the null direction, and that'll give us the thing we really are going to study, which is the response of this null energy operator to 2 insertions of the trace. Again, this can have contact terms, and those are going to be important. But an important simplification happened in going from here to here, which is that something that was all these complicated sum of nested commutators turned into just a Whiteman function. Okay, so the reason for that is that the ANAC operator, the null energy operator E, annihilates the vacuum. So if it hits a vacuum on the right or left, then it gives 0. This is a general property of positive operators, because if it did not annihilate the vacuum, then it turns out that you can very easily create linear combinations of vacuum and other states, which would violate the positivity condition. Okay, so we've reduced it to this form. Why look at the retarded correlator? This is sort of an unfamiliar object. Most quantum field theory calculations don't start with retarded correlators of the stress tensor 3-point function. So why are we talking about this at all? Well, we considered various things, and the real answer is that this is the one that worked. But in hindsight, I can motivate it as follows. So when we get to the discussion of the C theorems, the A theorem, what we're going to do is we're going to relate these contact terms to the conformal anomaly, and these non-contact terms, the separated contributions, are going to be positive by the ANAC when smeared appropriately. Okay, so in other words, when we take this correlation function and smear it over Minkowski space, somehow we can rewrite this as the expectation value of this operator inside some state. That's true because we chose this retarded ordering. We could have studied, say, the time-ordered correlator, which may have been a natural place to start. In fact, if you study the time-ordered correlator, you can derive some similar sum rules, but it is not quite right in order to get positivity. So it takes a little extra work. But the sum rules are very similar. The nice thing about studying the retarded correlator is that this combination here will directly turn out to be positive when we smear it. Okay, so let's come back to those contact terms. So contact terms are most often discussed in Euclidean signature, so let's start there. In Euclidean signature in position space, there could be delta functions in the correlator. Those are the contact terms. If we go to momentum space in Euclidean signature, then these delta functions will Fourier transform to things that are analytic in momentum. Well, there can be derivatives on here that I didn't write. So the derivatives on these delta functions will give polynomials in the momenta in momentum space. Now, if you Wick rotate this to Lorentzian along the usual contour, then you'll get the time-ordered momentum space correlator in Lorentzian. So one thing we can see immediately is that the time-ordered correlator in Lorentzian has contact terms, and that it's terms that are analytic in momenta, just as in Euclidean. But what about the other Lorentzian correlators? Well, there are various things that we can talk about in Lorentzian signature. We can talk about all the orderings, or we can talk about the Whiteman functions. The Whiteman functions do not have contact terms. So Whiteman functions, meaning you just you order these literally as written. In that case, you can't have any contact terms because in a Whiteman function, you can insert a complete set of states here between the two operators. And if you insert a complete set of states here, that can only be then you can only get contributions that are supported on the physical spectrum of the theory. So the physical spectrum in the full momentum is the forward light cone. So basically the positive energy condition of the quantum field theory. So Whiteman functions always have these step function things out front that force them to only have positive spectral density. And when you have step functions, you can't have anything that's analytic in momenta because it wouldn't satisfy the step functions. So the Whiteman functions can't have contact terms, but all of the other ones do. All the ordered ones do. The time-ordered, anti-time ordered, retarded, and advanced correlators. These are actually all analytic continuations of each other in momentum space, in complex momenta, which agree for some choice of momentum. So to give one example of this, let's look at the 2-point function. Say we have a retarded 2-point function of two operators O2 and O1, then it's just a trivial commutator identity that you can write this as time-ordered plus a Whiteman function. So I'm just expanding out the definition of this in terms of commutators and step functions. There's a time-ordered term and there's a Whiteman term, and the Whiteman term can't have any contact terms. So that means that the retarded and time-ordered have to have the same contact terms. And you can go to a region in momentum space where the Whiteman terms drop out. So the Whiteman term has to all come from finding some cuts in momentum space when you do the analytic continuation. So all these ordered correlators, and this also works for the higher correlation functions and for the other orderings, all these ordered correlators have the same set of contact terms up to some trivial factors of I that just come from the definitions. The contact terms in the retarded correlator are some factors of I times the contact terms in the time-ordered correlator, and those are the same contact terms that you have in the Euclidean correlator. So now we kind of see how this all fits together. It's pretty simple that all of these ordered correlators just have basically the same set of contact terms. Now I'm going to turn to the null energy operator and how it's related to the anomaly. So this calculation is going to be in conformal field theory. So we're going to first study CFT and then go to QFT next. Okay, so we're now thinking about a 4-dimensional conformal field theory. And we'd like to understand this object, the null energy operator, trace, retarded correlator at a conformal fixed point. At the fixed point, anything involving the trace has to be pure contact term. So these separated points type terms all drop out. We have to get pure contact terms. To calculate these contact terms, we're going to use a conformal anomaly. So the trace in a 4D CFT is given by this expression here in terms of, so this is the trace in some curved background. These are just all the terms that can show up by dimensional analysis. The first two terms are the conformal anomaly. So these are the ones that people always talk about. There's an anomaly term proportional to Euler, whose coefficient is called A. And there's an anomaly term proportional to Weil squared, the background metric, whose coefficient is proportional to C. Usually when people are talking about CFT, that's all they write. The other terms can be removed by counter terms. But we're going to need to keep them in this argument because when we actually, if we're just studying CFT, then we could just renormalize them away to 0. But we need to keep them because when we study RG flows, we're going to renormalize them away in the UV but they're gonna get generated along the flow. And so we need to keep track of them. So I'm gonna keep track of these non-universal terms. They have some coefficients, B1, B2, and B3, and lambda here is the cutoff setting the dimension.
Don't the third and fourth term just vanish by the equation of motion?
Well, we're not doing scattering amplitudes, so
No equation of motion, but then what am I supposed to, some bits of this, like the B1 and B2, the physicality of it. I mean,
well, they'll show up in correlation functions.
It's a background.
no. Oh, in the background, it's a oh, this is not dynamical. Okay, sorry.
Right.
Got it.
Yes.
Okay.
Yes.
Got it.
Right. Yes. Okay, so this is the stress tensor. This is the trace in some background metric. And to calculate the correlation functions involving the trace, you could just vary this with respect to the background metric. So this is the trace itself. You vary it once more, you get trace 2-point function. You vary it again, you get higher correlation functions. So if you do that calculation in 4 dimensions, which is a little bit of a mess, but straightforward, you can derive the contact terms in the retarded correlator of the average null energy condition, which is this object that we're interested in. Okay, so now I've just quoted the result here from doing these variations. So this is now the retarded 3-point function of the Anik operator, trace in 4D CFT. And there are a couple things to notice here. First of all, the first line is depends on the A anomaly. So there's an A, and then there's a K there's 4 powers momentum by dimensional analysis. The second thing to notice is that the other anomaly, the C anomaly, that one dropped out. And third, these counter terms, B1 and B2, are still there, but they have different momentum dependence as from A. So A comes with its own momentum structure. And that allows you to distinguish between the terms coming from A and the counter terms. And you can now invert this relation to solve for A. So think about this as a Fourier integral on the left, and we want to solve it for A. What we're going to do is we're going to take some derivatives with respect to these momenta to pick off this momentum structure, and then we're going to set K to 0. So this is actually the only term that has a K1 dot K2 in it. The counter terms don't have that one, so you can use this operator here to extract A. And now you've solved for A in conformal field theory, and you have this equation in the blue box. So in a 4D CFT, A is this integral of this light ray 3-point function. And again, since there's a trace in here, this is pure contact term we're talking about here. All this integral is doing is it's picking off the contact term that corresponds to A. So that's it for the CFT calculation. Now we're going to go to RG flows. Any questions?
Now we're doing
Yeah.
it for 60, so what's the problem if you repeat the computation from 60?
Well, there are various correlators we could consider in 6D. The most directly analogous thing one could do in 6D is to look at, you could do Anik trace, but there's no A in it, so that's hopeless. So the next thing you could try is Anik and 4 traces. And the problem with that is that the momentum structure you get from A is not independent from the momentum structures you get from the counter terms. So you cannot invert this relation. You cannot derive a formula like this. At least that's what we think at the moment. We're still working on that problem, but it doesn't seem to work. So one needs to work on
universal counter terms to B1 and B2.
Yeah, that's right. In the case, if you do Anik and 4 traces, then that's the problem that you run into.
This is a place where assuming supersymmetry is tough because some counter terms.
That makes sense. Yeah, right. Some things.
For example, the Laplace
might
squared counter terms obviously. Partially explain this.
Yeah,
How should you can help?
that's right. That's right. Yeah. It could be that one can do something more clever by combining other correlators or maybe inserting more annex, et cetera. But we haven't given up hope on the 6-dimensional one, but we just try to do this directly. That's the first problem that you're going to do. Okay, so now we can prove the A theorem from the NEC. So now we're considering a quantum field theory that flows between two conformal fixed points. High momentum is UV, low momentum is IR. M is just some mass scale for the RG flow. You can think of it as the mass of the stuff that's getting integrated out. The fact that it flows to these fixed points means that the trace in the UV agrees with the UV CFT. I've renormalized away the counter term, the extra terms, the B terms in the UV fixed point. As I said, they're now going to be generated along the flow. So in the IR, the statement is a little more complicated. We have to include the counter terms. The mass scale of the QFT plays the role of the, is the cutoff for the infrared CFT. So it's the mass that's getting in your way. It's this mass that's showing up in these counter terms in the infrared. So don't look at it yet. Okay, I'm going to say it in words because it's not that complicated, and then we're going to look at the slide. Okay, so the strategy is the following. We have derived this formula for the A in a CFT. We're just going to apply that formula to the infrared CFT. That's the first time. So A in the infrared CFT is this contact term in the infrared CFT. That's just what we derived before. But anytime we have a formula like this for an infrared quantity, we can think of that as the rule for the RG flow. Because that quantity that's generated in the infrared was generated in the QFT. So we can now reinterpret that as the sum rule. And the way we do that in practice is just to take this sum rule written in terms of the infrared CFT, and you can just immediately replace this IR CFT correlator by the QFT correlator. Going from here to here is just the statement that this QFT correlator agrees with the CFT correlator at order k to the fourth in the low momentum expansion. But the integrands here are two very different things. So these are equal, but that's the statement that you're flowing to this fixed point. But these are two very different integrals because the first one was pure contact term, whereas when we write it in terms of the QFT, that contact term is now being generated by an actual correlation function at separated points. So it's sort of blowing up the delta function into a separated stuff.
By QFT, you mean anywhere along the flow?
By QFT, the theory that's flowing. Yeah. Yeah. So now this integrand here has two types of contributions. It has its own contact term that came from the UV, and it has stuff at separated points. And this delta function that's being generated, the contact term in the IR, has a sum of two terms. It's a UV delta function, and then it's some separated stuff. So there's two contributions here. I'm now going to move the UV contact term to the other side. So we just take the UV contact term and move it over to the other side of the equation. That gives it AUV. So the contact term here is controlled by the UV fixed point. So that gives you an AUV on the other side. And then I'm going to use, I'm just going to expand out this definition. So now we have a retarded correlator at separated points, because we've isolated out the contact term. The retarded correlator at separated points, that's this expansion in nested commutators. So now I can plug in the nested commutators, simplify a little bit, and you get this formula in the box. So this is the key result, because this is the same sum rule that I wrote earlier. This is a sum rule that tells you the change in A anomaly along the flow in terms of an integrated 3-point function in the QFT, where this 3-point function has no contact terms. All of the contact terms, this is all at separated points, all the contact terms have been moved over to the other side of the equation.
When you say it's separated points, I mean, you're putting some cutoff there, or you're just saying because you remove the contact terms, it doesn't matter if you?
This is a Whiteman function, so it literally has no delta
Oh, okay.
functions. You can just do the integral. There's some technical difficulty with terms that are semi-local, but let me skip this. You can ask about it afterward if you're interested. As an example, let's think about the simplest RG flow. So the simplest RG flow that we can do in 4 dimensions is a free massive scalar field. So this flows in the UV to a massless scalar field, which has A anomaly written here. In the IR, the theory is trivial, so it flows to the gap theory with A equals 0. Even though the theory is free, the correlators of the stress tensor are actually sort of complicated because they're given by, because the stress tensor is a composite operator. But you can calculate these correlators by Feynman diagrams, and this is the calculation of the stress tensor or the null energy trace is given by this one loop diagram. And so you can calculate these correlation functions and plug them into the sum rule and make sure that everything's working. And it works. So that gives this change in A that we expected. This is just to make things concrete, show that we did our homework here. The sum rule works in this case. And the last thing I need to talk about is positivity, because we have not yet proved the A theorem. So far, what we did is we wrote this sum rule, but it's not obvious that this is positive. So this has a null energy operator in it, but the thing that's positive is the null energy when it's taken as an expectation value. Okay, so we need to apply the NX to some state in this form. That's the thing that's positive. Fortunately, it's pretty easy to write this in that form. So the sum rule suggests that we should try a wave packet with some kernel in the transverse direction, because we want to get an integral that involves some of these transverse coordinates x here. So we're going to try a sort of funny wave packet that's constructed by inserting the trace on the vacuum, smeared against a kernel that depends on the transverse direction. And we're going to insert it with some momentum in the null direction. This term here is just going to serve as an infrared regulator to make our state nice and normalizable. What's a little weird about this wave packet is that the integral is restricted to v less than 0, which is like half of Minkowski space. That's just because, well, we're trying to reproduce this formula here and as a v less than 0, so that's the wave packet we're going to use.
So in all these formulas, U is like x0 plus x1?
Yes, the U and V are the, yeah, exactly. If you're familiar with the Hartman-Melisanic conformal collider setup, it's useful to compare. So in their case, they have in mind something that's kind of like a collider experiment where you study a state created by inserting some wave packet here near the origin. That's like where your scattering happens. And then you measure it in a calorimeter at far away. So they think of the detector, which is this NX operator, as inserted at Scri plus. This is a picture of Minkowski space. So here's your wave packet, and then you measure things up at null infinity. What we're doing here is a little bit different because we really need the wave packet to hit the light ray operator, to hit the detector. So our wave packet looks like this. We're doing a wave packet just over a half space, and then inserting the NX operator straight through the origin. This is a correlator of separated points, but if you zoom out, imagine doing this from very far away, then this is a contact term in the infrared CFT. So that's sort of how they're related. Once you have this wave packet, you can relate it to the same kind of correlators that we've been discussing and calculate the null energy in this wave packet. The leading term at low frequencies is a positive number times delta A, and therefore the NX implies the A theorem. AUV is bigger than AIO.
Can you drive anything else interesting by using different weight packets?
No, we haven't succeeded in deriving anything else. So the thing we tried to do was to derive some inequalities on the counter terms. So those would not be a statement about CFT. Those would be just a statement about RG flows because you'd have to have the RG flow to calculate the counter terms. The problem we ran into had to do with this technicality that I skipped about semi-local terms. So we haven't managed to isolate any interesting other statements in 4 dimensions. We can get some interesting other statements in 2 dimensions, which I'll mention briefly in a second. So I'm going to wrap up with a couple of comments. First, let me briefly compare to Komargatsky and Schwimmer. So in Komargatsky and Schwimmer, which remember is this original derivation of the 4-dimensional A theorem, they used a very different type of technology. They coupled to a background dilaton and then studied the scattering amplitudes of the background dilaton. In particular, they use this d phi to the 4th type constraint, which uses positivity of the cross section plugged into a dispersion relation like this one, and they related delta A to this dispersion relation. So what does this have to do with our sum rule? Well, it's not clear. We don't know the answer to that in detail, but it's very suggestive because, well, they calculated delta A and we calculated delta A, so we could set these 2 formulas equal. And what that's telling us is that there's some relation between this smeared Anek correlator and the dilaton forward scatter. And this looks like the Lorentzian inversion formula in CFT and some analogous things that occur in QFT. Because the Lorentzian inversion formula in CFT relates, well, in that case, it relates light ray operators on the left to double discontinuities of CFT correlators on the right. In this case, it's relating light ray operators to scattering amplitudes. But I think this suggests some role for Lorentzian inversion-like formula now for non-conformal theories and the scattering amplitudes of the background fields showing up on the right. This is just a particular term in that inversion formula, but there's probably a bigger story here where you can extract various, where you can compare the Wilson coefficients and these light ray type integrals. The quantum info perspective, I think I'm going to skip this and just mention the results that are special to 2 dimensions. So in 2 dimensions, most of what I said is very similar in 2 dimensions. There's one important difference though, which is, well, the formulas are a little different because the anomaly is different. The steps are about the same. But we can do a little better in 2 dimensions because in 2 dimensions, the average null energy is related to the null momentum. There's some extra assumption here going in here about the boundary conditions. But under this assumption, the average null energy operator is just equal to the momentum generator in the u direction piece of u. And that means that we can very easily calculate correlation functions involving not just one of these Anek operators, but any number of Anek operators because they just act as derivatives. So you can do not only the single Anek, but you can insert any number of Aneks inside your correlation function. This gives you the following concise statement. So we take the general QFT 2-point function in 2 dimensions, then these stress tensor correlators by dimensional analysis are, well, Z here is, I've reverted to 2D CFT notation. Z is like U. Z is one of the null directions, but I'm writing Euclidean language. So this is given by some by dimensional analysis, 1 over Z to the 4th times some function, some form factor that depends on Z bar, and M squared only in this combination. And what you can show by this argument is that f is what's called a completely monotonic function of m squared. So a completely monotonic function is a function whose derivatives have alternating signs. And this is something that mathematicians have studied and characterized functions like this. The proof is very simple. You just insert n copies of the average null energy operator inside this correlation function, and it comes out immediately. In particular, the Zamolodchikov-C theorem comes out of this argument for n equals 1, and it just comes out immediately by inserting the momentum operator. It's actually a little easier even than Zamolodchikov's derivation. He had to do some cleverness of combining conservation in various ways to get the C function, whereas here you get it immediately by inserting this operator. All right, and with that, I will conclude. So to wrap up, light ray operators are a useful probe of the RG. 6 dimensions we had some discussion of. There are 2 issues. One is the one that we talked about, where you have to get the counter term, you have to find some universal way of extracting the anomalies that's not contaminated by counter terms. Even if that worked, there's another obstacle, which is positivity. Okay, so it was really important that we were studying 3-point functions here, because the thing that's naturally positive is a Whiteman function. And the thing that naturally has anomalies in it are the ordered correlation functions. Now, it happens in the 3-point function that you can relate these to, but if you had, say, some rule for a higher point function, it would be hard to show positivity. So even so really, there's 2 issues that you have to overcome to get this working in 6 dimensions. One is dealing with the counter terms, and the other is dealing with positivity. Those both need to be solved. So this case is still open, and I think C theorems are still fascinating and mysterious, and we need to understand them better. Okay, thank you.
Say something on the semi-local term.
Sure. Yeah. So well, first let me go back to the derivation. So when we did the derivation, we applied the sum rule to the infrared theory, and then we moved the contact terms over the other side. But I glossed over the possibility that there could be terms that are neither contact terms nor separated terms. Those are the semi-local terms. So semi-local terms are terms that have some delta functions and some separated points. They come from operator valued contact terms in the OPE. So like if you have an OPE that has some operator times a delta function, then you plug this into a 3-point function and you get something with partly separated, partly delta functions. If you had any terms like this, then that would ruin the argument, because we really needed to have contact terms plus separated terms without any of this junk. But miraculously, they drop out of this calculation using some special properties of the light ray operator. So using the fact that the ANAC annihilates the vacuum, you can get rid of a bunch of these potential. Basically, what you do is you write down every possible semi-local term that satisfies the unitarity bounds, and then the only ones that satisfy the unitarity bounds get killed either by the fact that we're looking at the null component, that kills a bunch of them, or the fact that the ANAC annihilates the vacuum, that kills the rest. And there just aren't any semi-local terms that you can write in this correlation function. So that was a miracle that had to happen for the argument to work.
Could you take a reasonable guess for 3 dimensions by inserting not x1, not x2, but the square root of something?
Well, in 3 dimensions, we can't even start because we don't have an anomaly.
But what happens to the formula or some modification of it? See. Yeah.
Well, I don't know the answer, but what I would like to try, I haven't tried this, but what I would like to try is to maybe study the Anik and de Sitter space. The reason I say that is because of this quantum info argument of Cassini and Huerta. So they study the theory on a 3-sphere. Well, it's related to they study something that's related to putting the theory on a 3-sphere. Now, in our case, we won't. If you want to try to relate that to the Anik, you have to go to Lorentzian signature. So something that seems like maybe it could be connected would be studying the Anik in 3-dimensional de Sitter space. Whether you can get a summable or anything, I have no idea, but that's what I would try.
The annoying thing is that, well, perhaps you're giving up on the idea of having a formula for F, but just one for delta.
Right. Right.
So what's next for you and your research on these C theorems, proofs, etc.?
Well, we want to understand. We want to keep trying in 6 dimensions. As the naive thing doesn't work, but that doesn't mean that's impossible. There are the various combinations of stress tensors and null energy operators that one can consider, and maybe we just have to be a little bit more clever with finding the right combination. The other thing that we're trying to understand is the relationship to the work of to the perturbative C theorem. So there's this whole literature going back to Osborne and Osborne and Jack from the 90s, where they proved in perturbation, they proved the A theorem in perturbation theory. And that's also been done in 6 dimensions more recently by Sturgeon and someone else. What's missing at the moment is a clear connection between these perturbative A theorems and the work that I discussed. And we think that thinking about all this in terms of light ray operators might be a useful way of understanding those results. So those are the main things.
Hopefully, maybe you or your colleagues could find like a general theorem for these, for even dimensions at least. I don't odd dimensions, since you said there's like no anomalies in 3rd dimension.
Yeah, the broader problem of like C theorem, understanding C theorems, it would be really nice to have a more universal explanation. I feel like in the end, the answer should not involve anomalies. That since anomalies are specific to even dimensions, that the ultimate proof of the C theorems probably should not involve anomalies. If I had to guess, it'll be something more operational, something more like what people use in quantum information, like some operational way of defining degrees of freedom in a quantum field theory. But I'm not sure how that'll relate to light ray operators. Yeah.
What is the relation between the expressive form of the unforgiving probability and the other physical equation? What is
Not very specific. In CFT, the answer is that the forward limit of the correlator, so if you have a 4-point function, then there's some forward limit where 2 of the operators come together, and you can use the OP to turn them into a light ray operator. My feeling is that this should be something similar, that you should somehow be able to think of 2 of the operators, something like deep inelastic scattering, where you think of 2 of the operators as probing the other operators, and they probe it through the exchange of this light ray operator. Roughly something along those lines, but in detail, I don't know.
In your earlier work, didn't you have some like higher spin Anik type operators? Do those get you anything? Maybe try to use them in this context? or-
Not that we know of. Yeah, there's a higher spin NX, which says that the lowest dimension operator of any even spin has an NX-like inequality. But the problem is that in an RG flow, we don't have any way of calculating that from the anomaly. So that spin 4, let's say the spin 4 one, that spin 4 operator does not even have integer dimension. So it's not gonna have anomalies when you stick it in with the trace. So I wouldn't know how to get started. Maybe in particular examples, like in these perturbative flows, those will have some interesting interplay with the trace because they'll have integer dimension. But in the general case of interacting theory, it's hard to see how to study those.